Oh, students, right here again today. Notes for section 12.2, Newton's first and second laws of motion. Took quite some time for the relationships between force and motion to be developed. It states over 2,000 years. Aristotle, one of the first guys to work with forces and motions, he proposed incorrectly that force is required to keep an object moving at constant speed. This is incorrect. He made many different scientific discoveries through observation and reasoning. Galileo corrected some misconceptions that had been held since Aristotle's time, and this was roughly over 1,500, 2,000 year period. So Galileo corrected many misconceptions. Galileo worked with how gravity produces constant acceleration. He rolled balls down wooden ramps, and if they were not subjected to friction or any other force, they would continue to move indefinitely. Newton expanded on work done by Galileo and other scientists. He defined mass and force and came up with his laws of motion. Published his work on force and motion in a book called Principia. Hey, here's one of our key questions. How does Newton's first law relate change in motion to a net zero force? According to Newton's first law of motion, the state of motion of an object does not change as long as the net force acting on it is zero. Unless an unbalanced force acts on an object, the object will remain at rest. Object remains at rest. Unless an unbalanced force acts on motion, an object in motion remains in motion with the same speed and direction. This all relates to a property called inertia, tendency of an object to resist a change in motion. So you'll want to remember the first law, and just remember it's the law of inertia. And Christ sequence dummy, this next few slides are going to show inertia. As this car crashes, it's going to run into the barrier. Car is stopping, but the crash dummy is going forward, and it will continue to go forward until something stops it. Seat belt, much better thing, or airbags, much better thing to stop a person if they're going to crash than the windshield. And then here we get to Newton's second law. Newton's second law of motion, the acceleration of an object is equal to the net force acting on it divided by the object's mass. Newton's second law, we get a nice little formula down here. A equals F over m. Another common way you see this formula written is F equals ma. Mass defined here to be a measure of inertia of an object. And acceleration, directly proportional net force acting on it, and it's also its mass. Acceleration of an object always in the same direction as the net force. And again, force, another vector. When that force acts in a direction opposite to the object's motion, we get a deceleration, or causes it to slow down. Acceleration depends on the force and inversely on the mass. So, same force causes a single cart to accelerate 8 times faster than a chain of 8 carts. So, small mass, big acceleration. And if we got a big mass, we get a smaller acceleration when we apply the same force. Here we get a little example problem. Automobile with a mass of 1,000 kilograms accelerates when the traffic light turns green. If the net force is 4,000 newtons, what is the car's acceleration? Like always, we identify our information. So we got mass equals 1,000 kilograms. Force equals 4,000 newtons. And we want to know what the acceleration is. So I mentioned earlier that acceleration equals force divided by mass. So A equals the force is 4,000 newtons. And when we put newtons in here, we're going to write it as a kilogram meter per second per second. And we divide that by 1,000 kilograms. Kilograms divide out. A 1,000 goes into 4,000 4 times, so our acceleration is 4 meters per second squared, and it does need a direction, and we don't do any specific direction in here, so we will just say forward. Author of our textbook, it goes through this. It identifies the information. What are we trying to find? Get a formula, replace, substitute in, and do little calculations. The other example problem, a boy pushes a cart of groceries with a total mass of 40 kilograms. What is the acceleration if the net force is 60.0 newtons? Again, force equals 60.0 newtons, identifying some information. Mass equals 40.0 kilograms. Trying to find acceleration. Formula A equals F over M. So A equals force, 60 kilograms meters per second, breaking Newton down into what it means, divided by 40 kilograms. Kilograms divide out. Need to do 60 divided by 40, which would be 1.5. Keeping proper number of significant figures, we'll put it 1.50 meters per second squared. And once again, we'll just say forward. This one, they do give us a direction in here, upward. Give us a mass, and give us a force again. So, mass, 5,000 kilograms. Force, 10,000 newtons. Trying to find the acceleration, which is force divided by mass. Acceleration equals 10,000 kilograms meter per second divided by 5,000 kilograms. Kilograms divide out. 5,000 goes into 10,000 twice. Nice easy division. So the acceleration is 2 meters per second squared upward. This time, we see our mass of 1,200 kilograms. An acceleration of 3.0 meters per second squared forward. And we want to find the net force. So our base formula again is acceleration equals force divided by mass. Rearranging that formula a little bit, we get force equals mass times acceleration. And to find one on top, we can just multiply the other two. So force equals mass, 1,200 kilograms, times acceleration of 3.0 meters per second. Do a little multiplying, and we get 3,600. And we've got 3,600 kilograms meters per second squared, which means we've got that's kilograms meters per second squared is a newton, so 3,600 newtons. And our direction is forward. Another example problem. This time we see a 25 Newton force. Gives us an acceleration of 0.5 meters per second squared. And we want to know what is the mass. So our base formula again, A equals F over M. We rearrange this formula to, we want to find M. So M equals F over A. Remember, when we're trying to find this one down here on the bottom, we can just take these two things and switch them. So, here we get mass equals force, 25 newtons. We'll switch to newtons to kilograms meters per second, divided by the acceleration, which was 0.5 meters per second. Then the seconds divide seconds divide seconds, mass, or meters divide meters. We're left with kilograms, good unit. So then dividing 25 by 0.5, divided by 0.5 will be the same as multiplying by 2. This will be 50 kilograms. Then we move into, we'll talk about mass and weight. Mass and weight are related to each other, not the same. One definition of mass, or description of mass, measure the amount of material an object contains, where weight is the force of gravity acting on an object. Weight is the product of mass and acceleration due to gravity. So the formula we get is W equals mg. just a specialized version of Newton's second law, F equals ma. G, 9.8 meters per second squared, and then we get this weight formula down here. Another good example problem. Here we've got a mass of 112 kilograms, and it tells us acceleration due to gravity, or G, is 9.8 meters per second squared, and we're trying to find the weight, and W equals mg. So the weight is 112 kilograms times G, which is 9.8 meters per second. Little multiplying, 112 times 9.8 is 1097.6. If we round this to the right number of significant figures, we're going to get 1,100. And we got kilograms meters per second squared, which is newtons. So our weight is 1,100 newtons. So gravity changes, illustrated here on the Earth and on the Moon. Mass is the same, but weight is different because gravity is less on the Moon. It turns out to be about, on the Moon, acceleration due to gravity is about 1/6 that on Earth. So astronaut, or on the Moon, something would weigh about 1/6 what it does on the Earth. But the mass remains the same. So another key question, how are mass and weight related? Mass is a measure of the inertia of an object. Weight is the measure of the force of gravity acting on an object. And a few real review questions. What is inertia? And here you just need to remember that inertia is the tendency of an object to resist change in its motion. Calculation problem, 3,600 force, acceleration of 4 meters per second squared, and we want to know what the mass is. A equals F over M, so M equals F over A, and we do all the work out, we're going to get 900 kilograms. Question 3, how would your mass and weight change if you're on the Moon's surface? Said this one just a minute ago in our slides, and we figured out your mass would remain constant while your weight would decrease. That completes section 12.2 notes. Next time we'll be on 12.3. That's all for now.